Okay. Work out the energy levels, energy eigenvalues of the one-dimensional harmonic oscillator using the Schrodinger equation and a ladder operator method. The Hamiltonian operator, the Schrodinger equation is basically just an eigenvalue equation where the Hamiltonian operator acts on the wave function and gives you the energy eigenvalue, and the wave function is an eigenstate of the Hamiltonian operator with that energy eigenvalue. Our Hamiltonian operator is defined as the potential energy, which is a function of the position operator, plus the momentum operator squared over 2m. It's basically just a quantized, an operator version of the regular classical setup. In our one-dimensional situation, our momentum operator, here I'll write it over here, see it, is just negative I times h bar over the position, or the first derivative with respect to x, which is position. And in that case, when you square it, you just get the I goes to negative 1, h bar squared times the second position derivative with respect to x. So I should fix that there. And in our case, the harmonic oscillator is defined by its potential energy, which as a function of x, which is position, 1/2 m times w squared times x squared. That's not totally important, it's just part of the formalism. It's yeah. So in our case, that leads us to the Schrodinger equation. We basically need to find the eigenvalues and eigenstates of an operator, which is the position operator squared, we need to find the eigenvalues and eigenvectors of this operator right here. The most common and simplest method to do that is using ladder operators. A lot of books don't really actually go over, how they got these ladder operators. So one day I just was, toying around and I came up with this. So I'm going to derive these ladder operators. The concept is, I'm going to erase all this beautiful stuff. The concept is that suppose we have some operator, we'll call it A hat, and it acts on a state, or on a vector, or an eigenstate of the Hamiltonian. And when you act on that, here I'm not going to use Brock-Hettner notation yet, you get another different eigenstate. Now the original eigenstate only had the eigenvalue of E, and this new eigenstate, we'll call it nah, we don't need that. Has the energy eigenvalue plus the difference between them, delta E. Alright, so, okay, this is where we'll cut something out. Okay, so in that, another way of putting this is that when you act the Hamiltonian operator on this new eigenstate, which is A hat acting on psi, it equals another eigenstate, but with the eigenvalue E plus delta E, acting on the new eigenstate. It's a new eigenvalue equation. H bar. Okay. So we're gonna separate this out. We're gonna separate this side out. And this is E plus delta E acting on A hat. Well, the E is just a number, so it can be pulled onto the inside of this. Oops, cut off the head. Well, this little term right here is just our original equation, which is, so this term right here is just A times H bar, or A hat acting on H hat acting on psi, plus delta E times A acting on psi equals A, or H acting on psi. You can subtract off this side from this side and get this equation over here. Be unfiltered. We're just gonna be me today. Well, this is just the commutator of H hat and A hat acting on psi equals delta E A hat acting on psi. Circle that. Well, in principle, I can get rid of the size there, and we have this relationship here. The commutator of H, the Hamiltonian, with this hypothetical A hat, which when you act on it, on a certain eigenstate of H of the Hamiltonian, it gives you a different eigenstate with the difference in energy eigenvalue being this. That's basically what that means. So I'm going to use that. We're going to make an assumption here, and it turns out to work pretty well, and turns out a pretty lucky one. But since perhaps this A hat is equal to some combination of the position and the momentum operators. So alpha times the momentum operator plus beta, these are just little constants, times the position operator. And we're going to plug that into our equation. We know that our Hamiltonian operator is equal to 1/2 mw squared position operator squared plus momentum operator squared over 2m. So we're going to plug that into this equation over here. And so the commutator mw squared x squared plus momentum operator over equals delta E times AP plus BX. See how much easier this was once we actually got started. There we go. Okay. So, we're going to write this out into some components. So, we're going to separate this out because A plus B, C equals and we can pull out that little factor there. X squared. Wait, no, we can't. Not yet. Not yet. Don't listen to me. Wait, yeah, we could have. Plus 1, 2n you're seeing this correct, right? Okay, so I'm not blocking it most of the time, am I? Okay, good.
The only times you block it, anytime that you move away, I usually try to fill in.
Cool, thank you. Okay, so well, you can similarly break these apart in a decomposition like this. And pull out that factor of alpha plus beta 2. But this term right here is just the commutator of the position operator squared with the position operator itself. And terms like that, commutators, they go to 0 because you can expand that like that, and those commutator something with itself is just 0. So that first term vanishes, or that second term vanishes. And similarly with this part, the momentum operator and the momentum operator, that term will cancel and you're left with just the momentum operator and the position operator term. So we're going to write this out. Momentum operator squared. And pull out the factor of beta. Now with these, famously the commutator of the position operator with the momentum operator is equal to IH bar, and you can see that because of let's do this little distraction over here on the other side. So let's act it on a test function. Let's say f right there. And we know that the momentum operator is negative IH bar times derivative with respect to x. So we can just pull out negative IH bar x acted on a test function. So by definition, that would be that commutator there. And this, by chain rule, that disappears there, and you can break that apart as a product and get the derivative with respect to x times x. And that just goes to 1 because the derivative of x with respect to x is just 1. Well, those cancel out because those are equal to one another. And you're left with IH bar f equals position operator commutator with momentum operator times f. Well, you can get rid of the test function now, and you're left with that. So back to our problem. Okay, so the position operator squared the commutator with the momentum operator. We're going to decompose this like we would, get rid of the x squared and just describe it in terms of x and p. Well, these are just, we know that the commutator of x and p is just I h bar. So those are just numbers, so it doesn't really matter the order we put them in. It's just 2x h bar times I h, or what, x bar times I h bar is that term right there. That's a little ugly. Plus beta over 2m. Similarly, you're going to get a similar thing with this p squared and x. I'm just going to get px to momentum operator. The 2 is going to cancel out there. And that's actually the opposite of x and p. It's p and x, so it's actually negative I h bar. Yes, I'm using my finger. I don't have a dry erase marker yet, or an eraser yet. I don't have a proper eraser. I've been using paper towels or my finger. All right, so I'm going to rewrite this now. Calculated our commutator with the Hamiltonian and our operator, hypothetical operator a hat. Rewrite it up here. I don't like this. I haven't made an error. We're going to hope. I'm the momentum operator. So this is that commutator there, and it's equal to delta E times our operator. What was it? Oh, crap. Oh, good thing I wrote it up there, isn't it? Yeah, okay. Is equal to our operator. Now we're going to equate the momentum operator terms and our position operator terms, and equate the factors on them, because they're both of the form a times x plus b times p. Well, in general, constant times x plus constant times b. Gotta have that line underneath like my notes. So that means that delta E times B would have to equal I h bar times mw squared times alpha, and delta E times alpha equals negative I times h bar over m times beta. So we notice that beta, but we notice that beta is just, we can divide this whole part right here by delta E and just get that beta is this times alpha. So we're going to plug that equation into here. IH bar times negative IH bar mw squared over delta E over m. M's cancel. Equals delta E times alpha and the i's times negative I is just 1 because negative I is 1 over I, and that's just h bar squared. So we can tidy this up. H bar squared times w squared over delta E squared times alpha equals delta E squared times alpha. It would be kind of redundant if alpha were 0, so that would be very boring and wouldn't help us very much, so we're just going to cancel that out. And it requires that if there's some operator that can jump from one eigenstate to another, that our delta E has, and assuming that the operator is of that form, that delta E squared must be h bar squared times w squared. Now let's take the square root of each side. Delta E, but there's 2 square roots of this. There's not just one. There's positive and negative HW equals delta E. So there's not just one possible delta E. There's 2. There's when you jump from an eigenstate, you can either add 1 unit of HW to your energy, or you can subtract 1 unit of HW to your energy. So I'm going to. Oh, but we're also, now that I use a formalism when I'm doing this math, where I just replace the plus or minus sign with k. K is plus or negative or positive or negative 1. K squared equals 1 because that's what's in common with both values, and it just helps me do a more general, to keep track of it, which one I'm using. So delta E equals KHW, and K is either plus or minus 1. Well, now we can plug this into this equation right here. So KHW alpha equals negative IH over M beta. And cancel that little factor of H bar. And multiply both sides by M. And multiply both sides by I. No. KMWA. Yeah, okay, so, and you can pull out the KNW and say that alpha equals negative I over K. Well, 1 over K is just K, because it's either negative 1 or 1 in our situation. MW beta. And that forces our alpha and beta to have a relation. So our A hat is equal to some factor alpha oh wait, no, some factor beta. We're going to pull beta out. It just looks nicer. Beta times x hat minus I k over mw p hat. And that's just an arbitrary normalization factor. Basically all put together. Okay. Do I need any of this? Let's write it to the side real quick. Give me a minute. Oh, I should stress that because k is equals to negative or positive 1, there's actually two different operators. If k is equal to positive 1, then our energy has actually increased by hw, by a factor of hw. And if it's negative 1, it's actually decreased the energy by h bar w. And so when k is equal to negative 1, you actually get that, we're going to say that k is equal to negative 1. And k equals positive 1 equals to 1, you get the other operator. Now this means that this operator acts on a state and basically decreases its energy. So we're going to call it the lowering operator. And we're going to call this operator the raising operator. Because when it acts on an eigenstate of the Hamiltonian, it returns a state with raised energy. I've said that about 15 times in different ways, haven't I? Okay. We're going to return to our original system here. Like how I started to rewrite it over there, but then I just ended up backtracking and rewriting it on the other side.